Hello guys, welcome back to ptet.chemistry channel. So in this second lecture tutorials to complete off ionic equations, which I started out in the other first lecture tutorials. So we did precipitation reaction previously, where we covered these things on the formation of a solid precipitate by mixing in aqueous solutions, which was soluble previously. So in this continuation, we'll cover on other very key case studies of reactions that actually you could be asked repeatedly on writing out the ionic equations. So here there are three apparently completely different reactions. So they look completely different. Here you have nitric acid, HNO3. This is called lithium hydroxide. As you know, lithium is a group 1 metal, so you have Li plus and you have OH minus, so you have a methyl hydroxide, and it is called lithium nitrate, so you have Li plus and NO3 minus, and this is just water. This is hydrochloric acid, and this is sodium hydroxide. So sodium is just below lithium in the periodic table. In group 1, you also have this thing called hydroxide anion, which is OH minus. So you gotta be able to look out for this kind of thing. This is sodium chloride, one of your most important case study from giant ionic structure back in ionic bonding. You can recap and rewatch those lecture tutorials if you have forgotten your case study, which you shouldn't ever if you want to do well for Cambridge curriculum. This is water. The next one, example 3, this is sulfuric acid, H2SO4. It contains sulfate anion. This is the salt, K2SO4 is just K plus SO4 2 minus. So just a brief recap on how to get formulas from the charges on the ion. Group 1 ion, K plus is plus 1, SO4 2 minus, sulfate has a minus 2 ion. When you do the cross multiply, what you're doing is you're doing a LCM, a lowest common multiple that primary school mathematics actually taught you. So we are trying to balance out the charges. We are trying to see how many of these plus 1 do we need to balance out how many of these minus 2 charge. What is their meeting point? That's why we bring down the value. We never bring down the charges. We never bring down the ions. We bring down the value because there's our LCM. That's our lowest common multiple. And we bring down the value only, which is 1. What that actually means is I have K plus and K plus. I have 2 of the K plus and I have 1 of the SO4 2 minus, such that my formula is K2SO4, 2 of the K plus, 1 of the SO4 2 minus, because the minus 2 charge multiplied by 1 of it is minus 2, the plus 1 charge for both of them total up to plus 2 minus 2. The overall charge of the ionic compound is 0, and that's the objective of doing this exercise. So all these three are seemingly different reactions, but there's actually one commonality, one common factor for all these three equations, and that is to do with the idea of this is a nitric acid, this is a hydrochloric acid, this is a sulfuric acid, this is a hydroxide, this is a hydroxide, this is a hydroxide. Granted, they are all methyl hydroxide, methyl hydroxide, methyl hydroxide. Methyl hydroxide is what you consider a base or an alkali, however you want to pronounce it. I prefer to use the word base. You can use alkali. Acid plus base, acid plus alkali is what you call neutralization reaction, because you are trying to bring the pH to become neutral, because acid has a pH of below 7 and the base or an alkali has a pH of above 7. So when you react these two together, acid plus base, the reaction is neutralization because you're bringing them down to a pH of 7. So pH 7 on the right hand side, because there's the idea of neutralization. To neutralize the acidic environment, to neutralize the basic environment, you get pH 7, which is halfway in between the acid and the base, pH dividing point, which is pH 7 there, all right? So there's the commonality across these three seemingly different reactions, even though they are all different reactants and different products, but all of them do produce water, because you have learned that word equation. So I covered word equation a while back in one of my other lecture tutorial. Acid plus base will give you salt plus water, salt plus water. So this is a very, very important, I would say, a general equation. Okay, so the base comes from the methyl hydroxide. The acid will give you the name of the salt. In this case, it's nitrate salt from nitric acid, chloride salt from hydrochloric acid, sulfate SO4 2- salt from sulfuric acid. These are all from the very beginning of that lecture tutorial series, where I went through the name of the cations and the anions, and I also went through the names of the salt that we will get upon reacting acid with different substrate. That was in a couple of lecture tutorials ago. So in these reactions, everything is ionic, either a metal compound or acid in solution. Only the water is not ionic. Okay, so the rest of them, you can see there are ionic compounds, as I've shown you, Na plus OH minus, Li plus OH minus. Metal hydroxide consists of cations and anions, so it has a giant ionic structure. So the acid dissociates in water to give you H plus ions, and that is why, because you have H plus ions in water, your pH is lesser than 7. That is the definition of an acid. It dissociates in water to give you H plus ions. So each of these give you H plus ions, and you will get NO3 minus ions, such as these. You'll get Cl minus ions, such as these, and you will get SO4 2- ions, such as these. Alright, so this is basically showing down the nitric acid reacting with the lithium hydroxide. So everything dissociated into ions. Lithium nitrate, all nitrates are soluble in water. As I mentioned in my last lecture tutorial, all nitrate salts are soluble in water, and you will learn more of these when you come to solubility of salts, as well as preparation of salt topic under acids and bases, much later on in a couple of months, probably next year, I guess, depending on your curriculum. Okay, so all nitrate salts are soluble in water because you're producing lithium nitrate, so they're going to be soluble in water, aqueous and aqueous. The liquid water does not dissociate into ions, so you remain as such. And we talked about spectator ions previously. Whatever that appears in ions on both sides of the equation, we can cross out Li plus and Li plus. We can cross out NO3 minus and NO3 minus. We're going to be left with H plus aqueous, OH minus aqueous, and H2O liquid. So this is our ionic equation. This is our ionic equation. I like to write EQN for short form for equations, but just so you know how to interpret when I write EQN in the future. This is ionic equation for neutralization reaction. The next thing is to do with hydrochloric acid plus sodium hydroxide. Similarly, you get sodium chloride. All sodium salts are soluble in water. All sodium salts, potassium salt, ammonium salts are soluble in water. So this is another solubility rule which I talked about in the last lecture tutorial, but you will revisit these when you come to solubility rules as well as preparation of salts. Sodium salt soluble in water. Obviously, this is our table salt. And then we can cross out Na plus and Na plus, Cl minus and Cl minus. So we get H plus and OH minus giving us H2O. Again, that is our ionic equation for neutralization reaction. Hope you can see that these two are exactly the same equations. So despite whatever your reactants and your products, as long as it involve an acid and a base, you always have one ionic equation, which is H plus aqueous plus OH minus aqueous giving H2O liquid. That same ionic equation is the same ionic equation for every single acid plus base reaction in the world. Okay. So the next one is to do with sulfuric acid. So you have H2SO4, so you got 2H plus. You got KOH, which you needed to balance the equation. That's why you have two of them, which means 2K plus and 2OH minus. 2K plus and 2OH minus. K2SO4, meaning 2 of the K plus, 1 of the SO4 2 minus. 2 of the K plus, 1 of the SO4 2 minus. And 2H2O was just how you balance the equation just now. So we're going to cancel out the spectator ions, 2K plus and the 2K plus, the SO4 2 minus and the SO4 2 minus. Then you've gotten these equations, which looks different, but when you think about it, it's just multiple of 2, which you can divide by 2 to get simplest whole number ratio. So we want whole number ratio, and you can simplify it by dividing the whole thing by 2, and you get the exact same one, H plus aqueous plus OH minus aqueous, giving you H2O liquid. So you still get the exact same ionic equation for the neutralization reactions. Whenever you get an acid and a hydroxide, and of which the hydroxide is present in any base, or alkaline. So methyl hydroxide would be basic or alkaline. When you react with an acid, you will get H plus OH minus aqueous to give you H2O liquid, and that is just the ionic equation to show or to indicate that it's a neutralization reaction. And this is a universal language that links or that relates every single chemist in the world, irrespective of where you are, irrespective of what language you speak. This is the chemistry language that, you know, link us all chemistry students and chemistry teachers and chemists alike together. All right. Now there's another reactions which is to do with acid and metal carbonate. Just to briefly recap, when you have acid plus metal carbonate, you will get a salt, you will get a metal salt. The salt, the name of the salt, comes from the acid. The metal itself comes from the carbonate, the metal carbonate. And because it's a carbonate plus acid, you will get carbon dioxide plus water. Carbon dioxide and water are part of your structure and bonding syllabus, which you know carbon dioxide exists like that and water exists like that, with 2 lone pairs on the oxygen, and there's no lone pair on the carbon because it forms double bond to the oxygen, to each of the oxygen. It's called carbon dioxide. It's a simple molecule. You're breathing out CO2 as you are living and respiring, and you're also breathing out some water vapor because that's part of respiration. When you breathe onto a glass window, you will see some water vapor condensing outside because that's what you're breathing out as well. All right. Anyway, so we have 3 different reactions here again. This is a calcium carbonate, a group 2 calcium 2 plus, a CO3 2 minus, just in case you forget the formula of carbonate. So because these are plus 2 and minus 2, without even doing the cross multiply thing, you should be able to tell that you have 1 of each because the charges will balance out. In case you couldn't, then I will try and show you. You cross multiply and bring down the value. You do not bring down the charges, you bring down the value. So I mentioned about that a lot of times. The question now is, why is it 1 to 1? Because this thing can be simplified further into the simplest whole number ratio, which is 1:1. You can divide by 2 both sides or throughout, and now 1 to 1 means 1 of the calcium 2 plus and 1 of the CO3 2 minus, giving you this formula CaCO3. On the other hand, calcium chloride, you have calcium 2 plus and Cl minus. You can't do that because they are not the same charges in opposite manner. So you have to bring down the value on the charges, which is 1 and 2. So it means calcium 2 plus and 2 of the Cl minus. That's why the formula is 1 calcium 2 plus and 2 Cl minus, CaCO2. A lot of these should have become more and more natural to you unless you couldn't remember the formula of the common ions, which then I will suggest you to probably go back 5 or 6 lecture tutorials before this, when I actually cover the formula of ions and showing you how to use the formula of ions to construct or to obtain, to get the formula of these ionic compounds. So this is hydrochloric acid. You get a chloride salt. You get a nitrate salt from nitric acid. You get a sulfate salt from sulfuric acid. All nitrate salts are soluble in water. All sodium salts are soluble in water. This one you haven't learned yet, but I can tell you calcium chloride is also soluble in water. So all these 3 are soluble in water. We already talked about all nitrates are soluble in water previously, and all sodium, potassium, and ammonium salts are soluble in water. These are just general guidelines for the solubility rules, which you would learn eventually in your IGCSE or O-level or any 14 to 16 years old curriculum anyway. The idea in the ionic equation is focus on ions, and also what does not dissociate into ion. So when you have molecules such as CO2, they cannot dissociate into ions, so they will remain as CO2, And then you also have things like H2O, such as in neutralization, you will remain as liquid, you do not dissociate into ions. So you could start by writing CO2 on the right hand side and H2 on the left hand side. And how in the world do you get the CO2? The CO2 comes from the carbonate, which is present in all these three, so CO3 2 minus. There's something wrong. There's nothing wrong with this, so by the way, there's nothing wrong with this. You see how there's a solid there? Because this comes from these things which are insoluble in water. So these things are insoluble in water. I purposely didn't want to circle the sodium carbonate because the sodium carbonate can dissolve in water, as all sodium salts are soluble in water. But typically, you can think about that it can be solid from the solid carbonate that was insoluble. It can also be aqueous in the case of sodium carbonate, which can dissolve in the water, giving you the aqueous carbonate ion. All right. But the idea is that you have gas definitely and you have a liquid definitely. So I've seen cases where students or teachers would probably accept a solid. Ideally speaking, I should really probably change this to aqueous. It's better because even though these are solid don't react as fast. As soon as the surface gets into contact with the solution, it's actually the aqueous ions that will react much faster. It will be the aqueous ions that react and recombined with this H plus to give you these molecules CO2 and H2O. So we haven't done much here apart from just showing you the ionic equations. Of course, you could go back to the exercises where you could dissociate this into ions like 2Na plus, CO3 2 minus, 2H plus, SO4 2 minus, and then you get 2Na plus and SO4 2 minus, which you can cross out the SO4 2 minus and the 2Na plus. You'll be left with the CO3 2 minus. You'll be left with the 2H plus, giving you CO2 and H2O, which is the ionic equation for every single metal carbonate plus acid reaction in the world. So every single carbonate, every single time you see a carbonate reacting with an acid, they can only have this particular ionic equation. Let me think back. This is a tricky one because this is a solid, and that's partly because a lot of carbonates are actually insoluble in water. This is part of your group 2 metal carbonate chemistry. They are insoluble in water. That's probably why this particular author, this particular book actually specified that it's a solid, and I guess it probably depends on your questions, and you probably get away because this is a well-known book actually. I wouldn't specify which one, but this is a well-known book by a well-known chemistry teacher, a renowned chemistry teacher, and I'm pretty sure since this book is actually used by a lot of examiners as well in the UK, so this will have been accepted by any examiners after all. You probably see this in the marking scheme as well, this being a solid for the carbonate because a lot of carbonates are actually insoluble, and usually we don't react solution with solution. Sometimes, most of the time, we react a solid carbonate with a solution. However, if you have sodium carbonate solution, so you got to read the question, do you have solution reacting with solution, or do you have solid reacting with solution? This thing will never change because CO2 is a gas, H2O is a liquid at room temperature and pressure. All right. Last but not least, there's a reminder here. It's something called redox reaction, which is actually short for reduction and oxidation. Not a big deal at the moment, but redox reactions, redox equations, they tend to be combined together with this to try and confuse students. For the meantime, you really must understand the acid plus base, giving you the water, is the ionic equation for neutralization reaction. And the other one is just a carbonate and acid reaction, giving you the carbon dioxide, the water, and which we don't call neutralization reaction, by the way. But these two equations are what you should be able to write straight away, knowing what the neutralization and knowing what the carbonate and acid reaction does, so that you will not get confused when we come to reduction and oxidation in a couple of months' time. All right, so that's it for this lecture tutorial. In fact, I've gone through quite a lot of ionic equations in the previous lecture tutorial on precipitation reactions, and in this lecture tutorial we have continued on the two general common equations for neutralizations and the carbonate acid reaction. Don't forget to click the button on the bottom right to subscribe to the channel, and follow me at ptet.chemistry on Instagram, Facebook and Twitter. just to get connected and make queries and share with me how your learning is going and how your exam results are. And yeah, do share the channel widely with all your friends, your chat group, your study group, your relative, your juniors and your seniors from school, anyone else you think who will benefit from this 14 to 16 years old curriculum on my channel for the O-level and the IGCSE students, or any other curriculum in the world. Okay, I'll see you in the next tutorial video. Thank you for watching.